My name is Lucian Covarrubias,
And I'm Kyle Thompson.
and we're presenting a hybrid dynamic UAV which can leverage the energy-saving capabilities of a winged vehicle while maintaining the high mobility which we attribute to conventional drones.
With the popularization of autonomous delivery and transportation, there is a growing demand for efficient yet mobile autonomous vehicles. Hybrid UAVs, which can meet both of these requirements, may hold the key to pushing autonomous vehicles into the forefront of delivery, transportation, and long-term usages. In our project, we seek to use trajectory optimization in order to generate controls for a hybrid UAV which can execute efficient paths by utilizing both its VTOL and glider properties.
In order to implement this project, we needed to start with a model. The model which we chose has a great balance between sufficient propellers to enable high mobility and large wings to provide enough lift even at relatively low speeds.
We started with an open source CAD model and then edited the model to outfit it with control surfaces and joints in order to provide a higher degree of actuation, allowing for substantially increased mobility when in the glider mode of operation.
In order to perform any control techniques, we used the multi-body plant in Drake with the additions of propellers and wings to generate dynamics equations. Here you can see our model interacting with the simulator with spoofed controls, keeping it relatively upright.
In order to implement trajectory optimization, we needed to first design the control inputs to the system. We decided to use torque control for both the propellers and control surfaces. While we initially considered position control for the control surfaces, it seemed unnecessary to search over positions rather than torques for the optimization, so we reverted back to pure torques.
To perform trajectory optimization, we relied on direct collocation with a few initial constraints. Instead of an equality constraint on our final position, we created bounding box constraints which gave the solver a little bit more flexibility. Our margin in the z direction was significantly larger than those for x and y, which was vital to ensuring that the optimization would find a solution. We also constrained the positions of our plane to always be in front of our start and our z positions to always be above the ground.
For our first formulation, we added a large running cost on the squared power used by the vertically oriented propellers and a smaller running squared power cost on the horizontally oriented propeller. We also had a final quadratic cost on the error from the desired end state.
Our initial formulation had a few issues, primarily with a long solve time which produced noticeably erratic interim trajectories during the solution process. This also resulted in a suspicious looking trajectory which involved a very steep dive towards the final position.
We plotted a 2D projection of our trajectory, as well as the propeller commands. When looking at this, we noticed that the commands exhibited high frequency oscillations, while the horizontal propeller was barely activated.
We attempted to resolve this issue by changing cost values for certain propellers, adding or adjusting the distance from goal costs, but we still resulted in poor trajectories over and over, which resulted in a very unstable simulation.
In complete frustration, we decided to add additional running costs to the control surfaces used for gliding, so that we might be able to reduce the high-frequency control surface movements during stable flights. This suddenly resulted in significantly faster solve times, as well as much smoother trajectories. The propeller inputs and solution trajectory were much smoother after this change. In order to visualize the solution produced by the trajectory optimization, we utilized an open-loop control, inputting the solved trajectory of control points with a first-order hold between the knot points. We then simulated the trajectory based on the open-loop control and plotted it against the desired trajectory.
As can be seen, the drone is executing a pretty interesting trajectory without any constraints on pitch, but we can change this in subsequent trials. The success of this change allowed us to create tighter final position constraints while still being able to find a solution where we otherwise would have failed. While this trajectory diverges slightly more than the first, we can still do better by adding additional constraints.
Upon adding constraints on the orientation of the drone, we were able to produce smooth trajectories which don't exploit any complex maneuvers to reach the endpoint. In this trajectory, it's clear to see the successful navigation of the drone with reasonable pitch.
An additional benefit of this restriction is the very high degree of accuracy we received from open-loop control.
Through this project, we learned the limitations and quirks of the SNOP solver. We also learned that by adding certain constraints and costs, we could vastly improve the performance of the solver for our specific application to result in trajectories which leverage the hybrid nature of our UAV.